This is the second video of a three-part series on the rigid rotor model. As discussed at the beginning of the previous video, there are three fundamental model systems we tend to study in quantum chemistry. The first is the particle in a box, the second is the harmonic oscillator, and the third and final of these fundamental models is the rigid rotor. In the last video, part 1, we discussed a classical treatment of the rigid rotor, and here we'll focus on the quantum mechanical version of the rigid rotor system. The learning objectives of this video are to define the rigid rotor Hamiltonian, to draw a connection between the rigid rotor model and the physics of angular momentum, and lastly, to examine the nature of the rigid rotor energy levels, its quantization, and degeneracy among its states. In the last video, we discussed the classical rigid rotor, and there were a few key take-home points that we want to remember as we try to develop a quantum mechanical treatment of the same system. First, the rigid rotor model involves two bodies with two masses, m1 and m2, and those bodies are separated by a distance of r. In the rigid rotor model, we employ two constraints on this system. The first is that the distance r between the two masses is fixed, and the second is that the center of mass of our two-body system is also fixed. And we saw in the previous video that the kinetic energy can be written in terms of angular momentum L and the moment of inertia of this two-body system I, and that the angular momentum and moment of inertia can be related back to an angular speed and a reduced mass and the distance between the two centers. The starting point for our quantum mechanical treatment of the rigid rotor is to write down the system's Hamiltonian. As we've seen time and time again, the Hamiltonian is given by a sum of kinetic energy and potential energy operators. Since the energy should be independent of the orientation of the system, and since there are no external fields or interactions with any other bodies, the potential energy is zero. And so the Hamiltonian is given exclusively by the kinetic energy operator, which I've written down below as negative h bar square over 2 mu times the Laplacian. You'll notice I've used mu here, the reduced mass, and we're drawing this form of the kinetic energy operator from our previous description of a two-body system, the harmonic oscillator. Now the natural coordinate system for a rotating system is spherical polar coordinates, and so we can write our Laplacian in terms of r, theta, and phi. And you did this when you studied the previous math chapter in Macquarie and Simon. Copying the last line from the previous slide here, I can simplify the expression for the Laplacian by noting that in the rigid rotor system, r is fixed, and so all derivatives with respect to r must be zero. And that gives this slightly simplified version of the Laplacian. Using this form for the Laplacian and putting that back into the Hamiltonian gives the equation at the bottom of the slide. Now, if I copy that equation again to the top of this slide, I can pull 1 over r squared out to the first term, and I see that in the denominator, I have a 2 mu r square. And I'll recall from the previous video that mu r square is the moment of inertia. And so now my Hamiltonian can be written as negative h bar square over 2I times the terms in square brackets. Recalling from the previous video on the classical rigid rotor that the kinetic energy is just L squared over 2I, and remembering that our Hamiltonian only includes the kinetic energy operator here, we can determine that L squared must be given by the term on the right side of the bottom equation. Using the Hamiltonian from the previous slide, I can now write down a Schrodinger equation for the rigid rotor model. A couple of things to note about the equations on the screen now. First, you'll see that I've used the letter y to denote the eigenfunctions, not the letter psi. As it turns out, in the rigid rotor system, for reasons we'll talk about later, the eigenfunctions for the Hamiltonian are conventionally written as y. Second, since our Hamiltonian does not have any dependence on r, and only depends on theta and phi, we can surmise that the eigenfunctions will likewise only depend on theta and phi. And so you see here that y is a function only of the two angular coordinates, theta and phi. Now, the differential equation written at the bottom of the slide currently is not in a form that is easy to solve. To do that, we need to take two more steps. First, we need to multiply through on both sides by sine squared theta. And second, we'll make a substitution, shown in the bottom here, and we'll introduce a new term called beta. Carrying out those two steps yields the following homogeneous differential equation. And now we can impose boundary conditions on this system, and that will lead to quantization. Specifically, the parameter beta is found to have to be equal to very discrete values given by j times j plus 1, where j, which is now our new quantum number for the rigid rotor system, has to be equal to either 0, 1, 2, or some other integer greater than or equal to 0. Again, j is our rigid rotor quantum number. The wave functions that solve the differential equation and are eigenfunctions of our Hamiltonian are part of a special family of functions known as the spherical harmonics. And we'll discuss those more when we get to the hydrogen atom in a future video. For the time being, we're going to focus on what their eigenvalues look like. The eigenvalues can be found by going back to our original definition of beta, rearranging terms so that the energy E is written now in terms of beta, and then substituting j times j plus 1 for beta, remembering that j, the quantum number, has to be equal to 0, 1, 2, or some other integer greater than or equal to 0. And so now we see that the energy is quantized. The other result that comes out of a further study of the spherical harmonics and the rigid rotor problem, that again we will discuss later when we get to the hydrogen atom, is that we have many degeneracies that develop through the set of eigenfunctions and different eigenstates for this system. Specifically, for a given j, there are 2j plus 1 degenerate eigenfunctions. In other words, if j is equal to the number 0, then we have a single non-degenerate state, because 2 times 0 plus 1 is 1. But the degeneracy g sub j for j equals 5, for instance, is 11. When j is equal to 5, there are 11 degenerate eigenfunctions that all have the same energy. So to summarize this video, we recall that the rigid rotor provides a model for rotating systems, that the Hamiltonian can be written in terms of angular momentum, in particular the operator L square. And one thing I noted briefly, but I want to come back and emphasize here, is again, the Hamiltonian looks like a constant 1 over 2i times L square. And so the eigenfunctions of the rigid rotor Hamiltonian will be proportional to the eigenfunctions anytime L square shows up in our Schrodinger equations. The rigid rotor energies are quantized. We showed that. And we introduced the quantum number j, which is equal to 0, 1, 2, or any other positive integer. And finally, the rigid rotor eigenfunctions can have degeneracy. And the degree of degeneracy is given by g sub j, which is equal to 2j plus 1. Again, as the examples I gave a minute ago, for j equals 0, the degeneracy is 1. In other words, the state that you found for j equals 0 is non-degenerate. But if j were equal to 5, there would be 11 degenerate states. That's it for now. Our next video will look at how the rigid rotor model can be used to understand and to analyze the microwave or rotational spectroscopy of diatomic molecules. I hope everybody's doing well, staying safe, and staying healthy. See you all soon.